Here's our block diagram where the input is motor power in percent and the output is drive speed in RPM. Here's the schematic diagram of the system. We control the power to the motor, which leads into the gearbox that has a 100-to-1 ratio and then goes to the aerator. Here's the steady state operating curve where we got that our controller gain is 17.2% RPM per percent. Here's the step-up response from 70 to 100%. And the step-up response gave us an average gain of 17.3 RPM per percent and an average dead time of 0.1 seconds with an average tau value of 0.3 seconds. Here's the model step down from 30 to 5%. And that gave us the parameters 17.3% RPM per percent for gain, dead time of 0.14 seconds, and a tau value of 0.15 seconds. Here's the sine response with 1 hertz, and it gave us the time between peaks to be 1 second, and the delta M to be 20, and the delta C to be 250 on average. Here's our Bode diagram. It gives us an ultimate frequency of 4 cycles per second, K value of 18 RPM per percent, and a KCU value of 0.32% per RPM. Here's the feedback control, just a schematic of it. And here are the parameter locations for our root locus plot, which gave us that the ultimate controller gain was 0.47% per RPM. The quarter decay is 0.24. The critical damping is 0.05, and it's underdamped between 0.05 and 0.47% per RPM, and overdamped between 0 and 0.05% per RPM. The proportional only model we used the K value of 17.3 RPM per percent, dead time of 0.18 seconds, tau value of 0.05 seconds, with a set point of 300 RPM and a delta R of 100 RPM. This was the procedure we used to get our overshoot, offset, delta C, and settling time. Here's the P-only model results from the 5 to 35% region. This was critically damped and gave us a settling time of 0.3 seconds and an offset of 54. Here's the P-only model results with quarter decay, and quarter decay was at 0.311% per RPM for controller gain, and a decay ratio of 0.25 with a settling time of 0.5 seconds and an offset of 16 RPM. Here's the ultimate gain, and you can see that it's oscillatory with a controller gain of 0.474% per RPM. The P-only experiment parameters gave us, the time was 20 seconds with a bias of 18%, set point of 300 RPM, delta R of 200 RPM, and the time of step was 10 seconds. Here are the P-only experimental results for the 5 to 35% region. It gave us, this was with a controller gain of 0.03% per RPM, and it gave us an offset of 130 RPM. Here's a quarter decay with 0.1% RPM being the controller gain. It gave us a decay ratio of 0.26, settling time of 1 second, and an offset of 70 RPM. Here it is with the ultimate gain, where the controller gain is 0.2% per RPM, and it's oscillatory with a frequency of 2.875 hertz. The conclusions from the proportional only design are that the KCU is 0.2% per RPM, the quarter decay is 0.1% per RPM, the 10th decay is 0.08% per RPM, with the 1/500th decay 0.06% per RPM, and the critical damp decay is 0.03% per RPM. For our proportional integral design parameters, we use the TI of 0.3 and from the ultimate frequency of 4 hertz. We also ran experiments for TI equals 1.2 and TI equals 0.08. Here are the PI design results for the TI of 0.3 and gave the critical damping of 0.024% per RPM and the ultimate damping as ultimate controller gain of 0.24% per RPM. Here are the proportional integral design results. You can see that the 0.2 seconds and 0.7 seconds behave very similarly, but the 0.04 seconds is significantly smaller. Here is the 35 to 65% region, which gave basically the same results, and also for the 65 to 90% region. For the PI experimental results, this is oscillatory, and everything that we ran with the TI of 0.08 was oscillatory. And all of these graphs are going to have a controller gain of 0.12% per RPM. This is with the TI of 0.72, and it gave a decay ratio of 0.14 and a settling time of 0.8 seconds. Here is with the TI of 0.24, where the decay ratio was 0.25 and the settling time was 1.5 seconds. And here's a plot of the decay ratios for the 35 to 65% range. The TI of 0.08 is constantly oscillatory, that's why it's a straight line at 1. And then the TI of 0.24 and TI of 0.72 both behave very similarly, as I said before. The settling time, they also behave pretty similarly. They're on top of each other at the beginning, so you can't see it. And then over at 0.12, they deviate from each other. In conclusion, the PI design proves that the change in TI affects the controller gain less at higher values. And the settling times and decay ratios are very similar at higher values of TI, but low values create oscillation.
Good timing. All right, let's take a little bit of break and get something over here. What?
You can have it again.
I'm curious what you got over here. Can you help Fred with this?
Yeah. You okay if we put it right here? Where's oh, feta cheese and potatoes, macaroni and hamburger and sausage. That's not all for you, Pat.
Those are for me?
Not all for you. No.
Hey, that's a good time.
All right. That's bacon is gonna give us fun to get.
I guess I'll eat a piece of this pizza since I'm sitting right here.